Okay, welcome everybody to another exciting weekly Bootstrap seminar. Today we have Sasha Zhiboedov from CERN telling us about Conformal Collider telling time. Go ahead.
Thanks, Leonardo. Hi, everyone. Well, thanks for the invitation, and we are back to Zoom. I will tell you about a couple of works. We wrote a couple of papers we wrote recently with Grisha Kurchemsky and Emery Sokachev, and let me set the stage. So, Conformal Collider. What do we mean by that? Well, let's consider a collider experiment. For example, we can consider an annihilation of electron-positron pair into hadrons. And here, well, what we observe, some particles coming out, and we detect them. And when we think about the nature of the quantum state, which we are probing by this experiment, well, say in this case, we have some good idea that we create a photon which couples to electromagnetic current, which acts on the vacuum, and then we can think first in terms of partons, weakly coupled branching, and then hadronization, etc. But some more general question we would like to ask in this setting is that, let's say, given a more abstract theory and some quantum state which we would like to understand is how is the total scattering energies divided in the final state. So this question is pretty universal. It's effectively, if we have stress energy tensor, we can measure energy. It does not depend on existence of particles. It does not depend on weak coupling. I guess one thing which is here implicit is that this picture only makes sense in, say, d larger or equals than 3, so I need space, time, and some angle. Okay, this is not a good start here. Yeah. And now, of course, for this talk, I will just ask this question: how's the energy divided in the final state in the context of CFTs? And well, one obvious fact is that CFTs do not have intrinsic dimensionful parameters. Say, and what comes with it is that when you create some state here, let's say some particles, if they have a mass, if we have a mass, there is a natural clock attached to this mass, so a mass of a particle, and so if the particles are massive, then say we can expect that say for this experiment, maybe some correlations in time are hard to probe because they are very short. But one obvious question you can ask, okay, well, now I will focus on this question in a CFT and I will say what I mean. But you can rightfully say, but okay, if you're talking about CFT, we have correlation functions. We have, say, Whiteman functions, and this is all there is there, or it's a big part of it. So why do you talk about these collider experiments? And it's a legitimate question. And the answer I would give is that it's somehow, if you are given a Whiteman function, it contains a lot of information. But if you want to develop some intuition, you do not maybe care about the Whiteman function per se, but you want to know something about this Whiteman function. For example, if I give you a Whiteman function, you might ask, what is the Lyapunov exponent? And then you have an intuition, the theory is chaotic, strongly coupled, weakly coupled, etc. So the idea here is the same, that somehow we start with Whiteman functions, but by asking this collider question, it's a useful framework to reveal some of the properties of the theory, which are intuitive. For example, it is very intuitive to think here about the state having jets and how we think about the underlying Lorentzian dynamics. So even though at the original Whiteman function, what exactly does it mean that theory does not have jets is obscure. So here, this is the basic hope of this setting, is that we try to ask this question and gain some intuition, maybe to better understand the Lorentzian dynamics. Now, I can divide this question into sort of three parts. Is that first, for CFT, say, how do we describe natural detectors? then we can talk about, say, transverse structure. And by transverse structure, I mean structure of the quantum state or the, say, state produced by this Lorentzian dynamics and along the angular variable. So the structure of the jet, but we can also ask about the longitudinal structure. In other words, the state that you produce, if you measure correlations at different times, how are they, what is the structure of these correlations? And especially in a CFT where there is no mass gap, you might expect that, in fact, you can have correlations at very long times. There is no reason along this radial direction to somehow to have everything being kept. And while, well, the detectors you already heard, we already heard many talks and the stories, they will be related to light ray operators. And this transverse structure is the structure of the emergence and disappearance of the jets is related to the story of the light ray OPE. So we already also heard about it. But this question of longitudinal structure of the state hasn't been asked much. And well, I guess, say from the practical point of view, it's not an easy question, and but I think it's worth asking. Now, in fact, it has been, at least there were few papers, not many maybe, but few papers, and there was this paper by Hata, Yanko, Miller, and Triantafilopoulos, where they studied the jet evolution from weak to strong coupling in 2012. And they did ask precisely this question: what is the distribution of radiation, not only in space but in time as well? And they asked us by running some sort of deep inelastic scattering experiments. They started with a state, the state evolved in time, and then they put their probe at some point with some resolution, and they try to understand what kind of constituent the state has. And well, at weak coupling, I showed you the picture. We understand what are the constituents. These are the partons, but at strong coupling, we expect that maybe there are none. And this is indeed was the conclusion. If you look at the last sentence of their paper, they say the strongly coupled matter looks like a soft, smooth jelly. So now this is a very intuitive picture, and it's nice, but maybe we would like to understand a little bit better the properties of this jelly. And so that's what we tried. So we would like to probe this relativistic conformal jelly with light ray operators. So that's a basic idea. And so one way to think about it, it's some kind of deep inelastic scattering experiment, similar to what they did, but performed at null infinity. Now, let me be more precise. Again, we come back to this picture. We have some quantum state. Can be, well, for me, it will be local operator acting on the vacuum. It evolves, radiates, or branches, produces some radiation, and then we want to collect, say, if you're interested in energy, we want to collect some radiation at null infinity. And if we map it to the cylinder, like this, we naturally get an integral over light ray. So this is this integral. And therefore, here's this connection between detectors. If we want to collect energy and light ray operators, where the role of this light ray transform is simply it's an integral over the working time along which we collect this energy. Now, again, by thinking conformally, we can map this picture on the cylinder to some just null plane. Well, there is no preferred origin in conformal field theory, so we can imagine the origin being somewhere here. And then we can rewrite this operator, which here, say, n vector n labels point on the celestial sphere here at null infinity. So n belongs to this sphere. And the profile along with which you integrate along the scry is specified here by this function f. So this is a function along the working time. For example, if you just collect radiation from minus to plus infinity without any resolution, then you just set this function equals to 1. So this is an old good Leiter operator, but clearly this operator does not tell you anything about the structure. Say, it was the radiation presented here or not there. So it's natural to consider just a more general class of probes where you take this function to be non-trivial. So, and I guess in practice, this function depends on the funding, how long you can run your collider experiment, but for Conformal Collider, it's very cheap, so we can just choose this function at will. So here's the basic idea. It's very simple. So we would like to just generalize these considerations of event shapes being a matrix element of Leiter operators by including this longitudinal. I call it longitudinal because it's effectively probes the longitudinal structure of the state. Structure, yes, as this function f. Now, of course, you are free to choose this function f as you like. So, but let me motivate one convenient choice, which is nice. And this choice is dictated by the following things: that we can choose both detectors and states such that they diagonalize p mu. Now, for states, this is obvious. We just take a local operator, do a Fourier transform, and here you go. This state carries a definite momentum q. Now, for detectors of Leiter operators, it's a little bit less familiar, maybe, but it is true fact that if you take this operator and you place it at null infinity, so this integral over retarded time at null infinity, and you integrate it with some weight like that, then you find that these detector operators carry a definite momentum. And of course, if you set this omega to 0, you get back the usual colorimeter, which just simply measures total flux of energy. If you like embedding space, say in the language that Peter and David use in their papers, you take this light transform and you simply insert this phase here. So this was motivation from the point of view of just symmetries, but there is another important motivation, which is the following: that if you've thought about the world of the Leiter operators, it's quite subtle, and in the conventional particle physics, it's related to the issue of infrared divergences, but in conformal field theory, it relates to the behavior of this integral at infinity. And so in particular, because when you start computing matrix elements of these Leiter operators, you might find that, especially when omega is equal to 0, that you might get some divergences, and you have to be very careful to make sure that what you're doing makes sense. Now, by inserting this phase, we can only make things better. We cannot make things worse at infinity, or because this guy is bounded by 1. And so, in fact, a lot of analysis that we have done for the Leiter operators with omega equals to 0 in terms of bounding these matrix elements just go through immediately if you turn on this omega. So these are two important things. On one hand, we diagonalized p mu, and on the other hand, we didn't lose this boundedness of this factor at infinity just by 1. And in fact, in general, we expect it will damp things because it is oscillating phase at large u. So this is a motivation for our choice. I told you that here you can choose whatever f of v you like. And so here, for this purpose of this talk, I choose it to be a phase. For example, in the paper by Leonardo, Dalemil, and Simon and David, they also effectively consider some dispersive sum rules where they choose some function here, but it was different function, and I'll maybe mention this because they didn't care about this fact. Anyhow, so this is the setting. So at this point, what I would like to discuss is this light ray operators with non-zero omega. Now, let me do a little comment, because when I start talking to people who actually do some experiments and ask, well, how do we know in a collider experiments, how do we probe this structure of the state? And what I heard, so from heavy ion group here and also from Lance Dixon, that there is something called Hanbury-Brown twist interferometry. And in this case, you say you take a pair of identical particles, and because they're identical, they can interfere with each other. And you study a correlation function of these particles, of the number of particles with different momenta. And well, here you study it event by event. So this brackets is the average over events, and this brackets is average over the center of mass momentum, and you keep the relative momentum fixed. And somehow, if you think of some source of some quantum source of particles, and then you study their propagation, you see there are non-trivial interference effects. And people studied, say, in heavy ions, and they get these nice shapes. And then this is this function C is a function of momentum. And then by the widths, you can say what is the size of the source out of which things come out. At least this is my impression from a few, yes, from just looking at some of the basics. Now, if I think about it, yeah, we don't know what this observable. So this is an interesting observable. It's people care about it, but it's not clear to me what's this analog of this observables and would be in a CFT, because there is no natural notion of this number of particles. Maybe we can discuss energy. I don't know. But one important point is that when we talk about particle measured in a single event, we're still talking about some kind of probability and absolute square of the amplitude. So it's a sort of differential cross-section. You compute the amplitude and you count the number of particles with given momentum. So if you try to restate these matrix elements that I'm discussing here in terms of scattering amplitudes, you will find that this experiment is sensitive to the relative phases of scattering amplitudes. So now when we talk about differential cross-section, it's absolute square of the amplitudes, but in principle, there is a non-trivial physical information which you drop into interference terms. And these detectors, because they resolve time, effectively when the particle goes through such a detector, E of omega, you can have transitions. You can have transition where energy of before and after the detector is of order omega, and this is related to the resolution and time of order 1 over omega. And so in this way, in fact, if you just compute it using scattering amplitude, you see this related. The interesting thing is it related sensitive to the relative phases of scattering amplitudes, and I don't know what's a good practical way to measure those. But okay, this was the comment. Maybe it will be interesting to understand what is this interferometry for CFTs. Now, what I would like to talk about today is this couple of papers, and basically based on the introduction that I gave you, what we ask, we just like, okay, let's take some example and compute these generalized event shapes. So, and second is, well, let's study the commutator of these operators, and in particular at coincident points. And so, do they form some nice algebra, etc., etc.? You can ask these questions. And similar, partial motivation for this was because this has been discussed in the literature, but I guess let me emphasize again, is that people discuss in the past some of the operators of this type, where you just insert this v to the k inside the integral. But as I said, when you do this, you spoil the behavior at infinity. And in fact, most of the time, such integrals just do not make sense. They're just divergent. And you could have said, okay, well, let's take your plane wave, differentiate it k times, and set omega equals to 0. Isn't it exactly that? And you see that the fact that this object is ill-defined manifests itself in the fact that this object, this matrix elements of E omega, they are not analytic at around omega equals 0. So if you try to expand around omega equals 0, they are non-analytic there. So effectively, if you want to insert something like this, you have to specify from which side you are coming, from omega equals to from positive omega or from negative omega. In other words, this object by itself is not well defined. You have to regularize it. And so in my talk, we consider this object, this will be well defined, and so you can be safe and discuss them safely. And in particular, this light ray commutators also under control. In other words, this famous quote: "You should not simply expand the light ray in omega. It's not allowed. It's not just something very innocuous." And in other words, whenever this thing is not well defined, you will run here. If you just try to do it without much care, you might write into some paradoxes. And so, yes, it's better to work with objects like this, for example. Okay, so let me go discuss a little bit the properties of these detectors with omega. So again, this is the same things which I already told you. We consider this light ray operator, insert this phase. There is this longitudinal structure along scry and the transverse structure along the sphere. They carry definite momentum, and the matrix elements that we study are those. And I will focus on mostly on the two detectors, the simplest object of this type. Now, okay, what's the difference between these operators and the local operators? Let me remind you quickly. So if you have a local operator, you integrate it around over some bounded region, it does not annihilate the vacuum. We say that KT vacuum is separating. But these light ray operators, if omega is negative, they annihilate the right vacuum. And if omega is positive, they annihilate the left vacuum. Sorry, if omega is non-positive and non-negative. In particular, you see if you set omega equals to 0, they annihilate both vacua. And this is this famous properties that light ray operators with omega equals 0, they annihilate all the vacua. But you see here, for example, if you choose omega accordingly, you can also, when compute the matrix element of this guy, you can relate them to multiple commutators. Because if you consider a matrix element, some O, E omega 1, E omega 2 O, then you're just depending, and in general for non-equal n vectors, they will commute as before. So you can, depending on the signs, close it on the left and on the right, and write it as a double commutator. So this property that was present there, in fact, is still there. Now, again, for local operators, we know that the energy is not bounded from. There are states where the energy integrated of a bounded region can be positive or negative. And here we have average null energy condition. Now for this omega non-equal 0 guys, it's an interesting question how badly it can be violated, or what can be said about it. We haven't thought about, so I will not say much about it. I will not say anything about it. And finally, why do we like these light ray operators? On one hand, we got this nice properties that they annihilate the vacuum because they're non-local. So we're doing an integral which is not bounded. But on the other hand, they do preserve some nice structures that we like. Say the local operators, they commute at space-like separations, and these energy calorimeters, they commute also when they inserted at different points on the sphere, and this is based on causality plus Frege. And well, we discussed it in our paper with Peter, David, and Murat, and it's based on bounding the behavior at infinity. And just the point I want to make here is that inserting these omegas does not affect any argument, so you immediately just write this formula. It's the whole argument goes through. Now, finally, well, it was great to, so it was useful to write some kind of interesting sum rules. Well, if we have commutator of operators, we can insert a complete set of states and we get crossing equations. Here, if we take these commutators, we get some superconvergence, and again, we can generalize them. And for the OPE, we sort of understood what is the OPE for omega I equals 0. So again, I'm not going to talk about it. There was some structure that we have, if we omega equals 0, there is a bunch of light rays, and there are these selection rules. Now, when omega is not equal to 0, the selection rules will be gone. So you will not get these points, but maybe if you try to expand this omega around 0, I told you not to do it, but maybe there is a sense in which this light ray OPE can be generalized. I don't know, we haven't thought about it. Okay, so let me now just tell you, come back to my motivation, which is that I told you, well, let's look at the structure of this longitudinal structure of the state. And for the rest of the talk, just in view of time, I will focus on the holographic theories, because also they're somehow interesting. They exhibit interesting structure in this omega compared to weak coupling, maybe. And well, we just focus on some state created by a local operator, and we do some pair of energy detectors with omega 1 and omega 2. Now, what we actually did, we took the strong coupling, we took the resultant supergravity. So we studied these things in n equal 4 super-Young mills in Mellin space, and we used supersymmetry to go from to get this correlator with insertion of stress tensors. So this is just some technical details. I will not talk about it. It just can be done, and it's rather mechanical. It's kind of interesting that it still can be done, that even though you introduce this omega, things get more complicated, but you can do it in any case. So I will try to just focus, make a few comments on what we got, and discuss some maybe physics associated with it. Any questions at this point? Okay, I will proceed. So let's consider this object in n equal 4 super-Young mills at strong coupling. Now, I told you that if you, this is the result. I'm giving you the result. What is this result? Well, here you have this z. It's an angle. It's related 1 minus cosine chi over 2. It's an angle between detectors. And there are these two omegas, omega 1 and omega 2. In fact, you can introduce some dimensionless omegas in terms of the momentum of this operator. So this omega 1 and omega 2, they are dimensionless numbers. And this is the energy, E is energy correlator. Now, well, Subra is self-explanatory. Plus and minus refer to the fact that I told you these objects, they are non-analytic in around omega equals 0. So if you change the sign of omegas, they change quite significantly. And here, plus minus refer that this formula is valid when omega 1 is positive and omega 2 is negative. Of course, or 0, you can go to 0. If sometimes you will not be able to. Now, if you see that if you set omega to 0 in this formula, if you do that, omega 1 and omega 2, you get that EEC is equal to 1/2, and this is the Hoffman-Maldacena result, that the energy for 2-point function is distributed homogeneously, and no matter what's the angle between detectors, you get just the same result. Now here, this formula does not have some correlations, but okay, I don't have much more to say, but that it is there, and it does not have some dramatic properties so far. Now, one property that it has is that if you try to compute, for example, this commutator EEC plus minus minus EEC minus plus, and you take the derivative with respect to omega, and you set omega to 0, you would think, okay, well, what is this plus minus should not matter, maybe because omega is in the end is 0. But this is the simplest non-analyticity you can probe, and in fact, you see that already the first derivative is non-zero, and this is related to the fact that this result has maximal chaos. So the fact that the radial limit is related to the analyticity around 0, and the fact that the first derivative is non-analytic when you flip the sign is related to the maximal chaos. Now, this commutator, it's non-zero. So this commutator, because it's not really a commutator, it's a difference between different observables. It doesn't have to be 0 when n equals 1, when is not equals n equal 2. So even though detectors are separated, this is non-zero. And this commutator was computed in this paper. They observed this fact in a slightly different language, maybe, but that's my interpretation of what they have found. At least if I'm trying to connect to this language of omega, it seems to me that's what has been done. And this is related to the singular behavior of the corresponding correlator in the radial limit. Now, yeah.
So, can you remind us, how does it look in different dimensions, this property? So in d equal 2, aren't you supposed to be able to take at least 2 derivatives to put new and new squared, because those would be charges, or you're still not going to be able to do that?
Yeah, I think I'm in d larger than 3. Now, in d larger than 3, so in the non-perturbative CFT, this should be 0 because the non-perturbative radial intercept is less equals than 1. But because this is a 3-level supergravity, the radial intercept is 2, and this is translated to non-analyticity. So you're right that non-perturbatively this guy has to be 0, but in supergravity it is not 0.
Yeah. Okay, thanks.
Another property which you find of these observables, which you don't see when you set omega to 0, is that they exhibit bulk point singularity, and this is singularity. So now you see if you look at the supergravity result for plus and minus, okay, it is written here. Now, if you look at if you take both signs of both omega to be plus, the result is much more complicated. You can find it in our paper. It's computed there. But let me just point out that it has this feature that it has singularities of this type. So these singularities are absent at weak coupling, and you cannot reach them. I told you that here omega 1 and omega 2 are positive. So if they're both positive, you cannot reach the singularity really. But if you analytically continue them, you can. So it requires analytic continuation, and this is a little bit related. This is similar to what happens in de Sitter when you have a de Sitter correlators, the future boundary. If you want to extract a flat space amplitude, you have to analytically continue in momenta. So the same thing happens here. You have the singularity, but to reach it and to read off the sort of the bulk point limit, you have to analytically continue in omega. But you can check this property. Now, let me come back to this thought experiment that we discussed. So from the paper by Hoffman, Maldacena, and from the paper by Hatta, Janku, Müller, and okay, I'll not be able to pronounce the last author. We have this picture of this strongly coupled blob. It's a jelly, it does not have any structure. And if you look at the result of Hoffman-Maldacena, for example, let's say we take this omega equals to 0. So this is the result of Hoffman-Maldacena. It looks like, well, there is this 1, which is just this part of this blob. And then there is a small ripples. There is a small stringy ripples on top of this blob. But if lambda is big, this is a tiny effect. Now let's ask, what about the longitudinal structure of the state? And then also one interesting question about this quantity is, what about the quantum gravity corrections to this result? Can we discuss and understand those? Well, let's try to compute these corrections, and here you run into the following puzzle. Well, of course we will resolve this puzzle, and maybe it's not such a dramatic puzzle, but now we understand pretty well the structure of the correlator. So say from which the energy correlator comes from, which is that source, sink, and two detectors. So you do the light transform, you got the energy correlator. And so if you look at the paper by Shai, for example, he writes down the Snellian amplitude in full glory. And now you see the funny thing is that if you look at the, so this is a supergravity term, this is a supergravity. And this gives 1. Now you look at the leading stringy corrections, and what you find is that it has 1 over lambda to the 3/2. And if you look at the Hoffmann-Maldacena answer, it has 1 over lambda. So how come? Now the resolution is that, of course, we should think, well, really to first very roughly, when we're computing event shapes, what we are doing, we are taking a correlator and we are integrating it over time. And so effectively, when we integrate over time, there is some correlation length in time. And if it's very big, then it can change the power of lambda. And this is what happens indeed. And if you look at the stringy corrections, if you look at the stringy contribution to this energy correlator, it creates this long correlation in times, such that if you do them in perturbation theory, they in fact produce this divergence. So if you just computed this leading order result, you get the delta function. But if you go to finite lambda, you find that instead of this, well, of course, this delta function is nothing. So if you try to set here omega to 0 to compare to Hoffmann-Maldacena, so this is omega I equals to 0, then delta of 0 is nothing but just the integral over dt. And what happens if you do the computation at finite lambda, instead of this correlation infinite in time, you see that this integral gets regulated, and it effectively acquires a correlation from some large times of order square root of lambda. And so then you have the correlator is the size of 1 over lambda to the 3/2. The correlation length is square root of lambda, and then you get the Hoffmann-Maldacena result, square 1 over lambda from 1 over lambda to the 3/2. So in fact, this result is not just a small ripples on top of a blob. You see that this one does not have any, if you look at the correlations in time, they're just of the size of the wave packet. So if you measure the correlation in time and supergravity at infinity, somehow you will not find this very long correlation. But then you see the small ripple, which is correlated at very long times. So in fact, from this point on, from this sort of longitudinal point of view, this correction is not a small ripple, it's a very different in nature from this one. Of course, you don't see it at omega equals to 0, but if you go from omega equals to 0, you see that it's very different. Now, you can understand it also, well, you can write the dispersion relations, dispersive representation for this object, and you see explicitly how it happens. And it's usual story that you have some, well, here I wrote this energy correlator in n equals 4 is the sum of operators in the OPE for the sources of detectors. In fact, it doesn't really matter here. These are the sort of Polyakov blocks for this problem. And here you have this characteristic sine square coming from the double commutator. And then as usual, you see what happens is that if you have the sine square at finite CT, it's bounded by 1. But if you expand it at large n, you get this anomalous dimension square, and this grows with n to infinity, and you can get a divergence which gets regulated by 1. I guess this we can call, this is nothing but sort of iconalization in the usual context. So, but here in CFT it's very explicit. So when you have some phase which starts growing, but then you know that it has to iconalize, become sine in 1, and so you can see explicitly how this divergence indeed gets regulated, and effectively, okay, if you drop all these words, it's related also to the Regge limit, that if you consider Virasoro-Shapiro amplitude, its Regge limit is s to the minus alpha prime t, but if you expand in alpha prime at low energies first, you can get terms which grow faster. Now, there is an interesting comment, like, how does it happen physically? What is a physical picture for? Is there a way to think about this in some nice physical way? And there is a nice picture which we can draw at weak coupling. However, this picture is for the charge-charge correlator. So let me consider now the following process. We measure the charge-charge correlator in a state which looks like, say, a pair of particles, pair of partons. And then let's say one of these partons, it can be n equal 4, it's with weak coupling, for example. So it makes sense to talk about these things. And then one of the, say, quarks emits a gluon, and the gluons decays into quark-antiquark pair. And then you detect this pair with charge. So this, of course, this in n equal 4 quarks are charged, and so you put some R symmetry detector, then you measure the charge correlation. And now you see the following fact, that let's say this quark carries energy omega. Now, in the picture with detectors, what happens is that we put detectors at large separations, and they will detect this EPR pair. They will click because each of the quarks is charged, so they will click plus 1, minus 1. And as you start separating them further and further in time, what happens is that you want this quanta to be more and more delocalized, because, okay, they have to be correlated and very much delocalized in time. And so this corresponds to the fact that omega goes to 0 for this quanta. So when omega goes to 0, effectively this quanta become completely delocalized, and you can measure them wherever you want. But what happens is that if you measure charge, it does not care about omega. So they equally click no matter where they are and no matter how soft is this quanta. And this is precisely the mechanism which leads to the divergence. So if you try to compute the charge-charge correlator at weak coupling, the fact that you have these EPR pairs, which are very soft but charged, leads to the divergence, and this is related to the divergence in the Regge limit. Now, if you try to repeat the same experiment for the energy as opposed to charge, of course, the picture is now different, because if you put energy, as the quanta become delocalized, when omega goes to 0, the detectors respond less because they measure energy. And in fact, the whole thing is finite. So this is the usual story of infrared safety at weak coupling. But now this fact that we have this interesting correlation, APR pairs, say for the charge, what happens at weak coupling for the charge happens at strong coupling for the energy. So in other words, we see the same thing. We have an energy-energy correlator, and we compute it in perturbation theory. It blows up. Now, I do not have a similar parton-like picture how to describe for you a quantum state, which will exhibit this phenomenon that as you measure energy, the correlation does not decay. I don't have a good way to think about it in terms of partons. Well, we say that at strong couplings, there are no really useful partons, but somehow it feels a bit unsatisfactory. And now also, I told you that when we consider string corrections, we immediately saw that there is a scale where things are correlated at large times. Now, I don't know if it has any relations to the longitudinal strings spreading, but at least this is definitely a physical effect. So here I'm telling you something, usually at least I do not understand very precisely what is the longitudinal string spreading, but here it's a very precise effect. It's a statement that if you consider string corrections, in fact, you get these divergences, and this is related to the fact that you have a long correlations in this longitudinal direction. So now, let me now switch to the next, which is what about quantum gravity corrections? And let me remind you that quantum gravity corrections have never been computed for the event shapes. So if you want to detect quantum gravity at Conformal Collider, we don't know what to look for. What's the reason for that? Why they haven't been computed? Because there was recently a spectacular progress on understanding supergravity and loop amplitudes. And the reason is the following. Let's say you take one loop supergravity result for the Mellin amplitude and you compute energy-energy correlator. And let me set one of the omegas to 0 right away and keep another omega non-zero. And what happens is that you see that there are divergences in this 1 over omega. So there are log divergences. And therefore, if you want to compute energy-energy correlator, the first quantum gravity correction to the energy-energy correlator, you just cannot do it because the one loop result diverges. So you have to resum these divergences because we know that energy-energy correlator is finite non-perturbatively, and understand what happens to them. Now let me make one comment about this result. This is of course related to the fact that one loop supergravity is even more divergent than the Regge limit, and but we know that non-perturbative Regge intercept, it's more divergent than the tree-level gravity, but we know that non-perturbative gravitational intercept is less or equals than 1, and this corresponds to the fact that all these divergences should cancel in the end. Now let me make a comment because I somehow sometimes people say, or you hear that, well, the Regge intercept of tree-level supergravity of gravity is 2. Then at one loop from the iconal, it will be 3. Now you see me clearly, in fact, here is the leading result. So this result, the leading divergence, this corresponds to J0 equals to 5. So in fact, the Regge intercept of one loop supergravity in 10 dimensions is 5 at one loop. Why don't you, and the fact, and this Regge intercept from iconal, which is 3, is this term with log divergence. So you see that each power of omega is effectively reduces the intercept. So where is this 5 coming from? And here's what is nice. Again, if you look at this result, now you see what happens. What's the physical interpretation of these various terms? Well, first of all, let's look at this term. You see that dependence on Z is polynomial. In physics terms, it corresponds to the fact that it comes from zero impact parameter scattering in the bulk. So it's the same fact as if you have an amplitude which is polynomial in S and T. This is a contact term, and if it's a non-analytic and say T, it comes from non-zero impact parameters. So, and in particular, and also you can see that it's exactly the way it's regulated. There's exactly the same mechanism as was at work with Hoffman and Maldacena, and you expect, okay, this is a hard scattering. So the hard scattering, we know it's very soft in string theory, and we already know that effectively what should happen is that this omega becomes, so if we send omega to 0, we should exchange it for each 1 over omega to square root of lambda, which is this coherence time for a string. So you see that if you, okay, I haven't done the computation, but what you expect is that if you take the full theory now and you do the computation and you try to send omega to 0, you will find that instead of this divergence, 1 over omega square, you get an enhancement by a factor of lambda. Again, this is exactly the same fact that you have a hard scattering in string theory, which regularizes the growth of an amplitude. Now, the same applies here. This is also scattering at weak this is scattering at 0 impact parameters, and if you increase the energy, it's regularized by string modes. Now, what about this term? You see it's different because it has a log z, and this has different physics. This comes from finite impact parameters. This comes exactly from this iconal scattering in the bulk. And therefore, you expect it to get regularized by iconalization of the gravitational phase shift, which comes with G Newton. It does not come from alpha prime. If you take a scattering of two planets at very large impact parameters, it's iconalized by G Newton effects, not by string effects. So therefore, you expect that, in fact, in the full theory, again, if we are powerful enough to do the resummation, this term, which comes with log z, will become something like this. So the omega dependence, which is divergent, gets capped off in a non-perturbative theory with some time scale related to the central charge. So the difficulty of computing the quantum gravity corrections to this energy correlators at 0 omega stems from the fact that, in fact, the perturbative expansion of the correlator does not translate into the perturbative expansion of the event shape. You get this non-analytic terms in CT, you also get this enhancement in lambda. And so, again, based on this intuition and on this picture, we can make a guess what the leading correction is, and so leading quantum gravity correction to the usual energy correlator is, and it is the following. So here first you have this term which is lambda enhanced, and this comes from stringy effect, and this you can derive from dispersion relations. You just see that this has to happen, and in full theory there is some number here which we cannot compute, but this is pretty clear because we understand this effect relatively well, how anomalous dimensions behave at string theory, and how this sort of regularization happens for stringy hard scattering at 0 impact parameters. But then there is a natural guess you can write, which comes from really a gravitational scattering, and here there is log CT, and there is this functional term which satisfies all word identities. But again, deriving it would require understanding the all loop resummations of gravitational loops in ADS, and maybe this recent work by BC, Fardelli, and Jaundice, where they analyze some all loop effects, might be helpful, but we haven't done it fully. So coming back to our original question, we see that this Hoffman, Maldacena, and Hatta, Yanku, Müller, Tiantafilopoulos blob, it seems like when we probe it at null infinity, it has some structure naturally related to it. It has some stringy part, which is correlated with some scale squared lambda. It has also some quantum gravity part, which is literally, if you measure the correlations in your detector, you will find that they grow with time, for the time which scales with CT, and then eventually the correlation dies off. So this is a basic physical picture from the computation we did, and okay, I don't know to what. It would be nice to make it more precise, and but it has been already useful having this picture and understanding what happens to these divergences. For example, if you remove this omega, you just see that supergravity result is divergent, and it's somehow not clear what to do. So hopefully this can provide us some guidance. Now, let me say a few words about the commutators. I told you that these guys commute at separated points. What about coincident points? Well, at coincident points, you have a delta function. And let me write the answer for the commutator in holographic theory or in a 3D Ising, so it applies. And then you see that the only things that can contribute to this commutator are light operators. And in particular, say in these cases, holographic or 3D Ising, you get this energy detector itself and the delta function. Now you have an extra contribution here, which depends on this parameter NF tilde, which is simply roughly n phi over CT. And this is related to the three-point function of stress tensors. As you know, you can write it three different structures with some coefficients. And if your theory have an n phi non-zero, you will get this term in the commutator. Now, again, these functions, they're known explicitly, and they, again, simply show you that you cannot simply expand an omega, because they're non-analytic. You have logs. If you try to expand an omega, you get divergences in omega prime. So these formulas are not very well defined, close to omega equals to 0, or well. And to compare, so this is what the answer looks in, say, for 2D Virasoro. It's this term looks the same, this term looks the same, but there is no this term. Now let me make a few more comments. First of all, this is if you take an interacting CFT, there is no some miracle. No miracle happened at this point. It's not in fact, it's not really an algebra. It's a commutator. So if you try to check Jacobi identities, you will find that you will have to take into account all the operators, heavy operators. Here, all the heavy operators, sort of I dropped them because their contribution to the commutator is suppressed. But if you want to check Jacobi, you have to regularize, and they're suppressed here, but they will be more singular in the second commutator. So in fact, I don't think this is, we should think about this as some kind of algebra, generalization of Virasoro, or anything like that in 3D-izing. It's just a commutator which reflects on the low energy spectrum of the theory, which we can compute. Now, in 2 dimensions, it has some interpretation of Virasoro. What is its interpretation in high dimension? Let me skip the slide. Well, and I think here the interpretation is that there are the superconvergent sum rules. We can take this commutator, insert it in some correlation functions, insert a complete set of states, and then try to get some sum rules from this commutator. And in fact, exactly this sort of sum rules recently appeared in the paper by Leonardo, Dalmir, Simon, and David. When they discuss dispersive sum rules, they can be understood in this sort of sum rules. I don't know the role of these delta functions though, so so these terms were not important. I don't know if we can get some interesting extra sum rules from taking into interesting extra functionals which take care of these delta functions. My understanding that the functionals that we have been using so far, they do not reproduce correctly, or they're not sensitive to this commutator. I don't know if it's useful or not, but it's just a comment. Another little comment is that I told you this is not an algebra, but there are very specific cases where you can have a light ray algebra. And the very specific cases are free fermion. Sorry, let me, one comment here is that you could have asked, well, what if this n phi is equal to 0? What if this structure is equals to 0? But if you remember, there is a general argument from which it is expected that in any interacting CFT, in fact, all the structures are non-zero. So in fact, in any interacting CFT, you expect this structure to be present. So it will never look like this. But there are 2 CFTs in which this structure is absent. And these are free theories, theory of free fermion and theory of free gauge field. And in this case, you know that since theories are free, you have higher spin symmetry, and then higher spin symmetry, you can turn it into some kind of light ray algebra. And okay, it looks similar to W algebra, and it satisfies Jacobi identities, and we worked it out, but it is just a reflection of, there is no miracle again, it's a reflection of higher spin symmetry of the underlying theory. Okay, we massaged it in some way, we got something, but in interacting theories, the structure is not there. And another little comment is that if you consider free scalar, you also, the commutator does not look, so here the commutator looks like 2D Virasoro. This, okay, for free fermion. For free scalar, you have some extra operators that appears, and this again, some light rays, they by local in the field, you can construct them. So my time is up, let me finish. Okay, so this I think an interesting observables. but let me say that by going to this, considering turning on this omega, it seems like we can understand a little bit better this longitudinal effects, and in particular, we understand better how this perturbative non-analyticity of event shapes emerges, even at omega equals 0. Then there is this question. I told you that we have a understanding how to think about these quantum states in very intuitive terms. For example, if the usual words that are said, why do we have this Hofmann-Maldacena homogeneous distribution and strong coupling? Well, it's just because when you have a parton and you want to branch, it costs nothing. When lambda is large, it's very easy to branch. And indeed, then you think, okay, this blob is just a lot of soft quanta, they're branching and they're producing this distribution. And this correctly captures this intuitive picture, which immediately tells you without any computation that all endpoint functions of energy correlators will be 1 in supergravity. And let me remind you that even though we know this, we do not know the underlying stress tensor correlators. And here it's like immediate. So this picture correctly tells you the transverse structure, but this picture of partons does not tell you anything about this longitudinal correlations. And I don't know if there is some useful way to have some kind of gravipartons, so some kind of blobs, which captures this longitudinal structure and for the energy. And if we try to compute the amplitudes, recall that in the strong coupling, all the amplitudes have right divergence and the e to the minus area. So in fact, with some string tension, in fact, if we want to produce this event shapes by summing over correlators, we have to perform some integral over the area. And we don't know how to do that. So I don't know if there is any useful notion, but it's kind of physically puzzling how it happens. Finally, well, there are the sum rules, and I don't know. So I told you about this algebras. So there is this doubling group who are studying multi-stress tensors, and they're seeing some kind of also symmetries or potential algebra there. I don't know if there is. I don't see a relation. So I think what I told you about was very pedestrian. It's just some property of the OPE, but it will be interesting to understand. And maybe a more general comment. Let me end with more general comment is that, again, coming back to some intuition, let's consider a heavy state in a CFT. In fact, I'd show you this black hole picture, and when we want to run the experiment with the Hawking radiation, we probably don't want to measure the amplitudes, but the energy fluxes. So in fact, an interesting problem is to ask, what is this observables in heavy states in a CFT? And it seems like that they always to leading order factorize, and then there are some corrections. And it will be very interesting to understand how these corrections behave and how the micro properties of microstates encoded in these observables. But more generally, I think this is a kind of an interesting perspective because, okay, well, if we take a heavy state, usually the way we think about it is that we take it, act at the origin, it creates some homogeneous, say, thermal state on a sphere through ETH. It looks thermal, and so then we can apply thermal intuition to make claims. So even you cannot prove them, but you can apply thermal intuition to make conjectures. Now here, when you think about the same object in a collider frame, well, when you act with a heavy operator, it creates some very dense blob with many, as delta goes to infinity or delta becomes large, even in free theory, it will contain many quanta. And therefore, you expect that this if you take some finite number of detectors, then they will have to factorize. Just because you have many quanta, and there is a little chance that they are correlated. So this is some kind of not thermal but collider intuition about the same state. And in fact, at first they look quite different, even though they did the same things, but they look a bit different. It will be interesting to understand better what exactly is this collider intuition. So this is a conjecture, but it seems like there are things to which is a bit similar to ETH, but in a collider setup. It seems like there is an interesting questions to understand also about these heavy states, but more generally to understand this collider intuition about Viking functions and what can we learn about them from it. Sorry for going over time, I'm done.
Thank you, very clear. Any other questions?
Slava has a question.
Actually, sorry, it was a mistake. I just wanted to clap, but
Okay. Sorry.
a great talk, thanks.
Hi, Sasha. I can ask a question. So about this last comment. So what happens if you consider? I mean, is it useful to consider some blocks of the low-lying operators, say the stress tensor exchange in this say you take two detectors, just a 4-point function?
Yeah.
Which,
Yes. So then we can try to take the OPE, say heavy prime, heavy, light heavy prime, heavy prime, light heavy. Now I guess we can try to apply the ETH to those. And I don't know exactly how the map works. So usually this kind of formulas, we have an idea about them in this picture. And this formula, it's very natural in this picture. And what is the precise relation between these two pictures? I don't know, but it should imply something about the matrix elements of this guy. So I guess this factorized term comes from H prime equals to H. And what I'm saying is that all the non-diagonal terms, when we do the slide transform, the leading order should be suppressed. And in fact, I think for the free theory, I learned it from Riccardo Ratazzi and his master student. They did this exercise for free fields. And so they put 2-point function and they saw that it factorizes even in free theory. Well, in supergravity, it's trivial because things branch. And so this picture immediately applies. But okay, I don't know now that it's very tempting to say this is just always true in any CFT, in any heavy state. So the precise formula is delta heavy goes to 0 to infinity. We get this from +4 for 1 over delta heavy. But I don't know how to, maybe it's possible to derive it. It's not clear. It's just something which is very intuitive. Should be true.
Can I ask a question about this? Sorry, sorry for going again down to 2 dimensions, but in 2 dimension, isn't this is just true in both cases, right?
Well, in 2 dimensions, it's probably trivial, right?
Yeah, in 2 dimensions, like on the thermal side, it comes from the Schwarzschian.
Yeah.
And on the other side, it comes again from the Schwarzschian in another form. It comes from the recursion relation to the stress tensor. So there is there okay, so that's true, but what do we learn from?
Well, nothing in d equals 2, but what about d larger than 2?
Yeah, so the idea is I mean, I just want to say, okay, the fact that in d equal 2 is trivial, at least is a check that it can maybe.
Okay. Yeah. So maybe it's eventually trivial. Maybe it's somehow related to the fact that if we put 2 stress tensors here and the leading order, we just get a thermal expectation, and then the slide trace transform to nothing, or maybe even this is not true. I don't know. It's in all examples I know if this is true. Sorry, one interesting thing is that if you take a free field, then you have a state, which let's say kind of this black hole state being phi to the k. So you literally have k quanta. So we really know the microstates here. And now we can detect 2 particles and they will look thermal, kind of effectively. And then you can ask how many detectors you have to, well, sorry, by thermal, I mean just this. So you cannot say anything about the state. And you can ask, okay, how many detectors do I need to start distinguishing the microscopic structure of the state? And then you see that you need whatever K of order delta detectors. Then you start distinguishing some ripples. Of course, it's very toy model, but still it's kind of an interesting setup to ask these questions.
Sorry, Petra, you had a question?
Yes, I wanted to ask about the superconvergence part.
Yeah.
So, so you explained that the commutator of these two detectors is non-zero at even at is non-zero omega.
Yeah.
However, if you insert it into, sorry, it's zero, the commutator vanishes. But if you insert it into like a 4-point function, then depending on the signs of omegas, there is just one way in which you can turn this into a double commutator.
Yes.
So, and this is related to the fact that if you act with like E omega is positive omega on past vacuum,
Yes.
then
Yes.
that's
Yeah,
non-zero.
yeah, exactly. Yeah.
So I think that basically you can write E omega as like T of omega. So you just write Fourier transform stress tensor plus something which will annihilate the vacuum. So in other words, I think if you act with E omega, this positive omega on past vacuum, that's the same as acting with some multiple of stress tensor Fourier transformed just in the usual way without any fancy light trace at infinity. Just take Fourier transform stress tensor, act on the vacuum, because there is just one state in that the stress tensor can create with a given momentum, basically. And in this way, I think you can turn it into like this superconvergence into equality of two double discontinuities, but there is going to be a correction term in terms of some local 4-point function. Yeah, I'm not sure if that's useful, but I think this should be true. Have you looked at this at all? Or?
No, we haven't looked at the superconvergence. No. The only thing I looked is that is how does the sum rule from the paper by the guys about this dispersive sum rules is rewritten in terms of this omega a little bit, but just because it's as you said. So here, if you do the commutator, let's say fix the signs, this being plus and this being minus. Then if I insert it inside the 4-point functions, only for one ordering I can relate it as a double commutator. But for the other ordering, I cannot. But I think the sum rules at this, but then maybe it's related to what you said, but for certain choices of weights, then you can see that indeed you get some piece of double traces, but you can only say that you get the leading trajectory of double traces and nothing else. So this was this kind of subtracted dispersion. This was the subtraction and dispersion relations lead to the fact that the first double traces contribute. And this is related to the fact here that for one of the orderings, you do not get a double commutator, but you get almost double commutator. And maybe this is related to your comment, which I haven't fully understood. So maybe.
Right, thanks. That's interesting.
Any other questions? Okay, if not, thank you, Sasha, again.
Thanks for coming.
Bye, everybody.
Bye, everyone.